All right, this idea of a motion map or a motion diagram, it's just another way to express motion. Let's say that you have something that is right here. All right, so the dot represents its initial position at some moment in time, say 0 seconds. So it's here at that moment, okay? It's moving, it's crawling along the whiteboard to the right. And we're going to say that it's speeding up at a constant rate. So it's getting faster, continuously getting faster, but the rate at which it's getting faster, that's constant. So it's here at 0 seconds. And then 1 second later, it's moved over to here. So there's 1 second. Then after the next second, it's moved over here. Notice that it's gone further during that second because it's speeding up. Let's say after 3 seconds, it's over there. Okay? Started here, and it wasn't moving. It started at rest. Then after 1 second, it's here, and it is moving. Now this arrow is going to represent the object's velocity. And I'm going to say that after 1 second, it's traveling at 3 meters per second. At 0 seconds, it wasn't moving. It was 0 meters per second. Okay. Well, by how much did it change its velocity in 1 second? Well, it changed its position. Those are the green dots. It also changed its velocity. Those are the red arrows. It went from 0 velocity to 3 meters per second. That's a change of 3 meters per second in 1 second. Now, this change of 3 meters per second in 1 second is going to be a constant, and that's the concept of acceleration. Acceleration is the change in velocity, the rate of change of velocity. So during the next second, it would have gone from 3 meters per second to 6 meters per second. So the arrow gets longer, twice as long as that, right? Because if that's 3, this would represent 6. Notice that the change is constant, 0 to 3, 3 to 6. Each of those is a change of 3 meters per second. Well, then if it's increasing by 3 meters per second every second, then the next one would be 6 plus 3 is 9, right? So that would represent 9 meters per second. The red arrow represents its velocity at each of those points in time, 0, 1, 2, 3 seconds. The purple arrow will represent the acceleration. Now, classic question, we're studying uniform or constant acceleration. One of the questions that is asked, what is the acceleration at 0 meters per second? And at 0 seconds, and the velocity is 0 at 0 seconds, and they're at 0 meters. I'll call that 0 meters. So the initial position here will be 0 meters on this graph at 0 seconds. But what's the acceleration? And the temptation for many students is to put 0, and it's not 0. You cannot, the acceleration is the rate of change velocity, and if your velocity is 0, you can't go from 0 to 3 without actually accelerating. So you have to have an acceleration to get away from here. Okay? So the acceleration is constant. And I'm going to represent that with the purple arrow. So the acceleration is a constant 3 meters per second every second. Again, purple will be the acceleration. And notice that each one of these things is 3 meters per second every second. That's the acceleration. 3 meters per second every second. 0 to 3, 3 to 6, 6 to 9, 3 meters per second for every second. Now, we can express this as 3 meters per second squared, because that S, just FYI, this is meters per second times 1 over seconds. Remember when you divide by a fraction, you can flip it over and multiply. That's where the meters per second squared comes from. Meters times 1, meters, seconds times seconds, second squared. Okay. So let's go ahead and graph this thing. So that acceleration is 3 meters per second squared. Per second squared. These are called kinematic graphs or kinematic curves. Usually we just sketch them, but you should be able to interpret them all the same. Well, the position, I'll get to the position in a second. Let's go down here first. I'm going to do the velocity. Well, at 0 seconds, velocity in red. At 0 seconds, it has 0 meters. It's at 0 meters per second. At 1 second, I'll make that about here. It's traveling at 3 meters per second. So that's going to be somewhere like right there. At 2 seconds, it should be about here somewhere. Whoa, come back to me. At 2 seconds, it's traveling at 6 meters per second. Well, if that's 3, then that must be 6. Right around there. At 3 seconds, that would be somewhere about right there. That's up at 9, which would be somewhere around here. Okay, so that would be up like that. Notice that this is linear. Okay, and what is the slope of this thing? Let's start with that. Well, the slope of this, remember that's 9, that's 3. And so the slope is equal to 9 minus 0, rises from 0 to 9, so that's 9 all over a run. It goes from 0 to 3, right? So 3 minus 0. So that's a slope of 9 over 3 is 3, and this is in meters per second, the y-axis, so that's a rise of 9 meters per second all over 3 seconds, because of course time is in seconds, which becomes 9 over 3 is 3 meters per second every second, or 3 meters per second squared. No great surprise there. That's the acceleration, the rate of change of the velocity. Okay, slope of a velocity time graph equals acceleration. 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 Acceleration is defined as the rate of change of velocity. That's what the slope represents, the rate of change of the velocity. The area of this, what color will I use? Actually, hold on. Well, I have this 3 meters per second. Let's go down here and plot that. That's positive 3. 1, 2, 3. So here's positive 3 for the acceleration graph. That's the acceleration, the slope of that. And that's positive 3 the whole time, right? From 0 to 1 to 2 to 3 seconds, the acceleration is a constant horizontal line on a graph. Constant 3 meters per second for that whole time period. Okay. Something that you should note is that the area here, that would be 3, the area here, the area of that rectangle, 3 meters per second squared, meters per second squared, the area of this rectangle, 3 meters per second squared times 3 seconds is 9. The area, which in this case is 3 meters per second squared, times, because it's the area of a rectangle, times 3 seconds, is 9 meters per second. Well, that means that over 3 seconds, its velocity changed by 9 meters per second. So the area of an acceleration time graph equals the change in velocity. Okay? That's that time right there. The area of this represents the change in velocity. So a couple points here. Slope of this, slope of velocity time graph is acceleration. The area of an acceleration time graph is the change in velocity. Something that we've already talked about once before, but let's just point this out, is that the area of this is the change in position. So that area, it's a triangle, equals 1/2, it's a triangle, 1/2 base times height, or height times base, 1/2 times 3 times 9, right? Base times height. Well, 3 times 9 is what, 27, and half of that is 13.5. All right, 13.5 meters. So that equals delta x, the displacement, delta x. So this thing, in this time period, from here to 3 seconds, must go to 13.5 meters. All right.